Actually, while we are if you're trying to produce the ramp using a current source and a capacitor,
Okay, yes.
uh, uh, how to suddenly reduce IC by C to 0? Because yeah, the dVc by dt,
Okay.
if you charge a current capacitor using a current source, then if you have IC by C, we can get the slope dVc by dt.
Yes, it's correct.
So suddenly, after reaching the peak of the ramp,
Oh, yes. Then you want to
we have to make dVc by
it is 0.
yeah, the dVc by dt should be made to minus infinity
Yes,
because
yes.
it has to suddenly drop to 0.
Yes.
What is the way by which in a circuit we will do that?
I actually have not done much work on that. I actually just have a brief, don't exactly know, but okay. So you have your current source I0, then you have your capacitor over here. Okay, and this is your the voltage which comes over here is your ramp. Because it's a capacitor, it will integrate it. Suppose this was uncharged. Initially VC of 0 minus is equal to 0. Then then the current starts flowing, constant current, and it will start rising. Okay, then what you have to do is you have to reset it to 0. So you should have some sort of mechanism, some sort of you should say some sort of discharge circuit, okay, which will uh, come into uh, when this instant occurs, when it reaches the peak, then this discharge circuit should get activated and should discharge all the charge from the capacitor. It should discharge from here, and then after that you must again turn. Then after that your I naught must be again turned on. So exactly, I don't know. These are used in these commercial ICs. In these ICs will have some sort of way how to do it. So, but the basic thing is you have to have this I naught current to charge it. Once it is fully charged, this should not flow and it should get discharged from here. And once the discharge is over, then you start the I naught again and it should charge the capacitor. So there might be some sort of switches over here. Some sort of switching system might be there. Like that.
So, but at that time, if because we are switching off, we are discharging at a very small instance, so the current magnitude will be very high at that time.
Yeah, that is something. I don't know much about this actually. This is just some basic thing which I sort of understood. I've just skimmed through.
Okay.
Anyway,
Sir,
like
similarly in that,
okay.
Sir, in the current mode control,
Yes.
In current mode control, suppose in peak current mode control,
Okay.
if we operate a duty cycle less than 0.5,
Okay. Yes.
It is said the current loop is said to be having subharmonic instability.
No. For peak current mode control, if duty ratio is greater than 0.5, then it is unstable.
Okay. But the duty cycle should be approaching towards 0.5, sir, or it should be going away from 0.5. When will that subharmonic instability will happen?
Okay. Peak current mode control,
Or in both?
For peak current mode control, instability will occur when D is greater than 0.5. That is what you see theoretically. That is how you get it from the theoretical derivation. But even less than 0.5, like around 0.48, exactly these values I don't know, but it will start becoming unstable. Those subharmonics will start coming. So to overcome these subharmonics, you have something known as a
Sir, that subharmonic instability will be reflected in the wave shape of the inductor current, right?
yes,
Sir?
yes, in the wave shape of the inductor current. So what will happen is it will be like this, and then it will be like this and like this sort of. This is your this is your peak reference. Okay. So your inductor current and this is your time period. Okay, this is your uh just a minute, please. Okay. So let me just draw it again. So this is your peak reference, I reference, and your current will reach like this, it will become like this, and like this, and it will go on like this. So this is your time period. Okay, your time period is fixed, and this is the time for which it is on, this is the time for which it is on, and this is the time for which it is off. So what is happening is the time for which it is on is changing. Over here, the duty ratio will be like around 0.6, 0.7. Here, the duty ratio is around 0.3. So it is like unstable. But when you want actually, if it is a stable thing, it will be periodic. It will be like this. Waveform will be like this, like this. This is how we want a desired waveform to be. Okay. It will have like
So,
in steady state, the on time should remain, it should settle at a steady state value. But here the on time is oscillating from one value to another different value.
so after every, so instability means after every time period t, the inductor is not reaching to its initial value.
You could say in that sense. So what is the issue over here is it is on for some time and it is turning off.
Yeah. On time keeps changing.
Yes, it is turning off, and if there was no limit on the time period, it would have further reduced. But because it's a fixed
Yes, sir.
frequency, that is why it is again turning on. There's some sort of echo actually.
Also, the video is breaking.
Oh, video is breaking.
Yes, sir. Now it is still.
Okay. So this is a problem with fixed frequency because this time period is fixed. The current is not allowed to fall back. That is the issue with fixed frequency. So to overcome these sort of things known as subharmonics, we use something known as a compensation ramp. Okay, there's something known as a compensation ramp. In the compensation ramp,
Okay.
what happens is this is your reference. It will be further, there will be a sort of subtracting reference. Okay. Your reference initially is a straight line, but when you add compensation ramp, the reference is sort of decreasing with some slope, which is known as the compensation slope. So that stabilizes. So one suitable selection of the ramp for the compensation for the compensating ramp, suitable slope for the compensation ramp, then it will eliminate these subharmonics.
We are by making this ramp, we are trying to make the on time equal.
Yeah, it will make it equal. Any other query?
Yes, sir. Last class we talked. You explained that the peak current sensing is
Mm.
done on the top side switch, and the valley
Mm.
current sensing is done on the bottom side switch.
Yes, yes, yes.
In that, from your explanation, what I understood is
Mm.
the peak current when it is flowing through the when the ramp is increasing.
Now
If suppose you are doing peak current control,
Mhm.
sensing the peak current control, first we need to switch off the top switch, then we need to switch on the bottom switch. So that is the reason why we are sensing the switch on the top switch for the peak current control. Is that can I understand in that way, sir?
No, one. Okay. So talking about peak current control, right? So you have peak current mode control, and we have a buck converter. Okay, our buck converter is like this. We have our input voltage, okay, and then we have our switch. Okay, and this is my diode. This is my inductor. This is my capacitor, and this is my resistor. So this is my switch, which is controlled by my gate signal Q. This is my inductor capacitor. So my inductor current will be of this shape. It will go like this, it will go like this, go like this, go like this. And my current through my switch, the current through my switch will be like this. It will be like this, go like this. It will be some sort of value over here. Okay. The value will be here.
Okay, understood, sir. You can do.
Okay, so actually this is not zero. It will be like some sort of value. This is not zero, it is above zero. Okay. So this will come to the zero, it will continue like that. Again, it will start from this value and it will go on. So this is my current through this switch. Whereas my current through my diode will be the opposite, will be this current. So,
Yeah. Will be the falling ramp.
yeah, it will be the falling ramp. It will be this. This will be my current, okay, for my low side. No, current for my this switch, okay, for the diode. Okay. So if we want, there's our reference. Suppose our reference is like this. Okay, this is my reference. This is my reference. Okay, this is my reference. So I want my switch, this switch to turn off when the inductor current reaches this value.
Yeah. The high side switch to turn off.
Yeah, I want this switch to turn off. So I need to know when this inductor current reaches this value. I need to know when it happens. So for that, I need to sense this current. This current I need to sense for that. And that is why we do high side current sensing.
That is, we need to first we switch. If suppose it is a synchronous buck converter,
Yes, yes.
first we need to first we need to switch off this by sensing this. We need to switch off this high side switch and then switch on this low side switch.
Yes, yes.
So that is the reason why we are using peak current control for the top side switch.
That is why we're doing current sensing at the top side. See, there are three options. There are three options for current sensing. Okay, this will be taught in a further lecture, but I'm just telling you. One is I can sense the inductor current. Okay, I sense this current. So I will have a sensor over here. Here will be my current sensor. Okay, another option is I can only sense this current. That is the current flowing through my high side switch. Another option is I can sense this current. This is my current flowing through my low side switch or my diode. So there are three options. See, it depends on the application and various things. All this will be taught in the, I think, week 7. where we talk about the various sensors available. So that is explained: high side current sensing, low side current sensing, full current sensing of the inductor. So if it is not possible for us to sense the complete inductor current and we want to do peak current mode control, that is, we want to control the peak value of the inductor current, then we have to use this sensor. We have to use the high side current sensor. Because in that we have the rising slope of the inductor current, and when the inductor current reaches that maximum value, and when it reaches the maximum value, we want to tell the inductor current to stop rising. So we have to switch it off. So that is why we use high side current sensing for peak current mode control.
Okay.
Then any other queries or doubts? So today what we will do is we learned about the various control techniques, digital control, current mode control, voltage mode control, etc. And we also had seen certain simulations, etc. And now we will, and in those things we will have a KP, KI, KD, a PID controller or something. Now, how do we decide that value of the PID controller? That has not been taught. So that we will be covering in this session. This has been taught in the week 5, and I'll do a brief recap, and then we will study it. So we have a PID controller. Okay. PID controller has 3 parameters: KP, KI, KD. And how do we convert those gains from analog domain to digital domain, that we will consider. Then we will study voltage mode control. For voltage mode control, how we decide the gains. For current mode control, how we will decide the gains. We will see some questions also, we will check. Then also we will consider what is pulse frequency modulation, and if time permits, also time optimal control and large signal tuning. We will consider all these things. Okay, so yeah. Okay. So if you see this equation, this is my PID controller. This is my proportional part, this is my integral part, and this is my derivative part. Okay. What is a PID controller? This is my PID controller. It will generate an output U of t, and the input to my PID controller is VE of t. So this VE of t is the input to my PID controller, and the output is U of t. And the mathematical equation, this is a mathematical equation which tells how the error signal gets converted to a control output. So if we take the Laplace transform of this, we will get in this format. All right. This is the proportional, the integral part, and the derivative part. Now we want to convert. Yes.
No, sir. This is the PID controller for voltage mode control, right?
Oh, this is the PID controller equations. Okay. For voltage mode control, we use PID controller. For current mode control, we use, it is not required to have the derivative part. So we use PI controller or type 2 compensator. Okay, but
Okay, because
this
here
is
we have
just,
VE error is there.
okay, this is VE. Yes, yes, this is VE. Even for that also we use VE, right? For current mode control, we have the VE, right? So we will discuss, we will show. Okay.
Okay.
And then when we convert into discrete time, we get the following equation. So we are substituting here. What are we substituting? We are substituting S by 1 minus Z inverse upon T. Okay, if we substitute S by 1 minus Z inverse upon T, then we are converting it from analog domain, continuous time, to discrete time, and then we can get a PID controller. Next. So what happens? The control output also goes into digital domain. The error signal also comes into digital domain. And when we are performing these in discrete time, we don't use differential equations, we use difference equations. So this is the difference equation. So my u of n at the nth instant, my control output is divided into three parts: my proportional part, my integral part, and my derivative part. So my proportional part is given by this kp into v error of n. My integral part is given by ui of n minus 1 plus kic into ts into v error of n. And my derivative part is given by this equation. So this is how the PID controller has to be implemented in either my FPGA or my microcontroller or any other platform, digital platform which we are using to run this PID controller. So when you will write the code, you will write it in terms of certain of these equations, different equations, etc. Right. So when we show it in this form of a block diagram. So this is my block diagram of a PID controller. So this Z inverse is known as the delay. Okay, this is known as a delay. So V error of n gets multiplied by Kp, that's the proportional part, and comes out, its component comes out over here. Okay. This is my integral part. This is my integral part. So this is KID into V error of n, and this is UI of n, and it is delayed by a unit delay, and here is ui of n minus 1. So my ui of n is equal to ui of n minus 1 plus kid into v error of n. Similarly, for the derivative part also we will have ud of n. See, this is my ve of n, and because it is delayed by 1 unit, it will be ve of n minus 1. So this will be kdd into ve of n minus ve of n minus 1. Okay. So, and also what we found is the digital value of the derivative gain is equal to the continuous time value divided by the sampling time or the time period. And similarly for the integral thing, it is ki integral into the ts. Okay, ts is the period of the delay. Okay, how much the signal is delayed by what time, that is my ts, that is the delay. Right. So now we will proceed. We will use these for understanding of how we are translating our continuous time gains to digital, to the discrete time. So if you would have seen in the week 4, it was taught that a continuous time loop transfer function is equivalent to the discrete time small signal model transfer function. Only we must include a delay. We must include a delay in the continuous time. If we do that, then the transfer functions match. Then these transfer functions match. And we can design our controller. What do we do is we design our controller using continuous time. And then this continuous time controller is converted to digital domain using these formulas, and then they are implemented in our digital platform either by FPGA or microcontroller. Right. So that's the case. Now we will consider boost converter voltage mode control. So you guys are able to see the screen, right?
Sir, that delay is only TS, right?
Yeah,
That
yeah.
delay here, continuous time with the delay is the digital transfer function, small signal transfer function.
Okay, okay. This delay, there is one delay that is TD. Okay, that consists of digital pulse with modulation delay plus my ADC delay. that is another delay. I'm talking, this TS is the gap, is like the time after which I am updating. Like, we are going to store this value of UIFN and come out a UIFN -1. So how much is the difference of time between those two signals? That is my TS. Okay.
Mm.
So this is not, so this delay is not same as this delay. These are different delays. Don't confuse them. Okay. Yeah. Now we'll consider boost converter voltage mode control. So this is how a boost converter looks like, where we have considered various parasitic resistances, etc. And this is how the voltage mode control is implemented boost converter. We have a reference. We can subtract the feedback signal. That error goes to my controller that generates a control signal. So this is my control signal, which is compared with this RAM. Okay, it is compared with this RAM, and that generates my duty cycle. Okay, that will generate my duty cycle. So now we will try to find a loop transfer function. So how this entire system, we want to view it in terms of a control system block diagram. So when you will draw the block diagram, what we have to do? This part, as we have taught in the previous thing, this can be represented as 1 upon Vm. This is known as the modulator gain. Okay. Then, and this will generate the equivalent duty ratio. And that duty ratio will generate the output voltage. Okay. So that will represent in terms of block diagram. So this is my block diagram. I have my reference voltage. Okay. That, and then the output voltage. So the output voltage is subtracted from the reference voltage and it generates an error voltage. That error voltage passes through my controller, which generates a modulating signal Vm per term. That is passes through FM and that generates my duty ratio. That duty ratio passes through GVD and that generates the output voltage in terms of duty ratio. And the output voltage has three parts. The output voltage is composed of three parts. One is the component of output voltage due to my duty ratio. Another is the component of the output voltage due to my input voltage. Another is the component of output voltage due to my load current. So if you see, all these are perturbed. Okay, this is perturbed, tilde. This indicates a perturbed quantity. So V output will consist of a fixed V output, actual steady state V output, plus V output perturbed. Similarly, for each of these things. So in this block diagram, we are just considering these perturbed quantities. We are not considering these steady state quantities. Okay. So these are my perturbed quantities, and I will be using the block diagram to find out the loop. So when we are designing, when we want to design the, what you say, we want to design with a certain phase margin, with a certain bandwidth, then we have to consider a loop transfer function. Okay. So how do you find the loop transfer function? This is, if you see the system, this is my loop. Loop is a closed path. Okay. Okay. So in my closed path, what do I have? I have GC, I have FM, I have GVD. These Z output, GVG, they do not form a part of the loop. Okay. They are just external things. They're like sort of disturbances. But this is a part of the loop. So my loop is given by GC into FM into GVD. Now, okay, GC is my controller. Okay, this is my controller. This is my modulating gain, which is 1 upon Vm. And this is my GVD. So GVD for a boost converter is given by Vin upon 1 minus D square into 1 minus S upon omega RHP. This is my RHP 0 divided by 1 plus S upon Q into omega naught plus S square upon omega naught square. This is my GVT. Also, we have Fm is equal to 1 upon Vm. Then I have to have a GC. GC is my controller. Now the controller for boost converter voltage mode control, we use a PID controller. So PID controller is given by Kp plus Ki by S plus Kd into S divided by tau d into S plus 1. So this is the proportional part, this is the integral part, and this is the derivative part. So you will ask, why is this tau d of S coming into the picture? Okay, it was not there. So in an ideal PID controller, tau d is 0. Okay, it is not there. But in a practical PID controller, this tau d, it will come. Because to implement this derivative action, we use what we know as op-amps. We use op-amps. Okay, and they will have a bandwidth limit. So either the bandwidth limit comes inherently due to the op-amp, or we can forcefully set it also. We can forcefully set it. And why do we want this? Why do we want a band limited derivative action is because at high frequency there is noise. Their signal will have noise. So noise is not the useful part. Okay, the useful part is composed of a low frequency signal. Okay, but the noise is the high frequency components which are not useful, which will disturb our response, which will disturb our system. So we want to attenuate the noise. We want to attenuate. Attenuate means to reduce the noise. So to reduce that noise, we limit the derivative action with this tau d S plus 1. Otherwise, the problem with the differentiator at high frequencies, it is susceptible to noise, and noise can ruin the output. So that is why we use a band limited derivative action. Right.
Sir,
Yes, tell.
here if the tau d is 0,
Mm-hmm.
then the differential pole will be at minus infinity.
What do you mean by
S equal to minus 1 by tau d.
Okay, yes.
S equal to minus 1 by tau d. If tau d
Okay.
is 0,
Yes, correct.
then the pole will be at,
Okay.
pole will be at minus infinity.
Yes.
Sir, then which means at that time the damping will happen almost instantaneously. Is it, sir?
Yeah, like it's not damping,
Differential.
which is the derivative action. Yeah.
Okay. So derivative predominantly does the damping control.
Yeah. It improves the
Isn't it, sir?
damping of the system. Yes, you're correct. Yeah.
Sir, if tau d is 0 and we are saying if tau d is 0, that is ideal differential.
Yeah, ideal
That's why
differential.
we are giving some tau d value here. So what tau d is 0, what will happen to the response? And if we make tau d present like a non-ideal differentiator, how the response will change? What change will happen?
See, we whenever you would have studied Fourier series or Fourier transform, etc. So
Yes.
a signal, let us assume this signal, okay, this signal. It has a DC value, then it has a first fundamental harmonic, then it has the third harmonic, the fifth harmonic, etc. Right?
Yes.
But
Yes.
we want to limit our system to neither a DC component or only to the first harmonic and third harmonic. The rest harmonics we do not want it to come into the picture. If that is the case, then we apply a filter. Okay. The filter will remove out these high frequency components. Okay. So that is why this tau d of s plus 1, this acts like a filter. It will remove the high frequency components. Now, if tau d was 0, what it mean is it will act instantaneously. Okay, it will act very, very fast because the bandwidth is very high for the derivative part. If that is the case, if it has to act very fast, means it should act at very high frequency. But now we want to limit that frequency of operation so that the noise doesn't affect it. And so we place this tau d of s plus 1. So what will it do is it will slow down how fast the derivative acts. But our goal is this derivative action should occur for, let us say, the fundamental component. The fundamental component. If it is, our goal is that the derivative action should occur for the fundamental component. And if this tau d of s plus 1 is placed very far away, and this tau d of s plus 1 is designed to operate on the fifth harmonic, then it will not affect the fundamental harmonic response. Okay. So this meeting will end in 1 minute. Then we will proceed. We will start the meeting, resume the meeting again. All right. So please join in that one.
Sir, is it from what you are saying? Is it like a relation between the right? Sir, regarding this tau d, sir, are we talking something like the relation between time domain specification and frequency domain specification? The relation between rise time and bandwidth.
Yes. Yes.
So if the change is happening suddenly, then bandwidth is
If
lower.
no,
Is
no,
that
no. If the change is occurring very fast, that means the bandwidth is very high, so that the system is capable of responding very fast. If the bandwidth is low, the system cannot respond instantaneously. So band my bandwidth is inversely proportional to my rise time. So my bandwidth is very large, then my rise time has to reduce. My bandwidth is increased, my rise time will reduce. Okay.
So that's the same kind of explanation we can have for this
Yes.
tau d also.
Yes, a similar explanation can be helpful for this. So I will proceed. So what do we do is, okay, so these are certain expressions I write down over here. So this is our practical PID controller. Okay, this is the expression of a practical PID controller, and then what we do is GC, we make it, we will factorize this. So this part and this part we will multiply over here, etc. We will multiply. So GC will become KP into S tau D S plus 1 plus KI into tau D S plus 1 plus KD into S square. So this upon S into tau D of S plus 1. So my GC will become equal to KP into tau D of S square plus S plus KI into tau D of S plus 1 plus KD into S square. S into tau D of S plus 1. So we write it as GC is equal to KI, we take it as common. Then we get 1 plus S into KP plus KI into tau D. No, KP upon KI plus tau D plus S square into KP tau D upon KI plus KD upon KI. Okay, divided by the denominator. Any doubts in this part? Okay. So what we do then is so in this manner, and this can be written as K1 this can be written as K2, right? So that is how they write it as K1, K2. It is getting blocked over here. Similarly, so then this is my loop transfer function. Okay. What we have done is, this is my loop, this is my GVD of this. Okay. And all the DC components is clubbed into KL. They are not dependent on frequency. So this is the DC component of the loop transfer function. This is my GVD of S. Okay, GVD of S, this part, this is the DC part of GVD of S, and this has come over here. So this is the frequency part, frequency dependent part of GVD of S. And this is my controller's frequency dependent part. The DC part of the controller has come over here. Okay. So that way I am separating the DC part, and then the frequency dependent poles and zeros I am showing over here. Now I want to design my controller. So what I want to do is, I want to cancel out, I want to make dP of S to be equal to NC of S. If I make dP of S equal to NC of S, then this two will get cancelled. This will get cancelled and this will get cancelled. And if they get cancelled, then what I will get is K loop of S, I will get it to be this equal to KL. Okay, this will be equal to KL into 1 minus S upon omega RHP divided by S into tau D of S plus 1. This is my loop transfer function I get. If I do this pole zero cancellation, the poles of the transfer function of GVD are cancelled with the zeros of my controller. Right. So any issues in this?
You can proceed.
Now so we have done this pole zero cancellation. So we get rid of this format. Okay. What happens is, what they do is, they use tau D, they set it to be equal to 1 upon omega RHP. If we do that, my K loop of S will be equal to KL to 1 minus S upon omega RHP divided by S upon 1 plus S upon omega RHP. Now, why do I do this thing? So the advantage which I get by doing this is, this entire, sorry, what I get by this is, this entire part, this part, okay, will have a magnitude to be equal to 1. Okay, the advantage of doing it in this form is this has a magnitude of 1. So this will simplify my design. It will make my design simpler. Okay, that is why I use this method. All right. So I have done that. So overall, this will be my loop transfer function after doing all the steps which I have told earlier. Now what I will do is, I will substitute. Now I'm going to find a frequency response. Okay, it's a frequency response we have using Bode plot, etc. So what do we do is, we substitute S by J omega. So what I will get is K root of J omega. This is KL. Okay, this is my KL. So this will be KL into 1 minus J omega upon omega RHP divided by J omega into 1 plus J omega upon omega RHP. Alright. So now I want to make the design simpler. So what I do is, for omega, I will write omega upon omega RHP is denoted by the term omega n. So omega will be replaced by omega n into omega RHP. So my K loop of J omega will be equal to KL to 1 minus J omega n into J of omega n into omega RHP into 1 plus J omega n. So this will not be K loop J omega, it will be K loop J omega n now. Because I'm replacing omega by omega n into omega RHP. Omega RHP is my constant. Okay. So I get K loop of J omega n to be KL from omega RHP into 1 minus J omega n by J omega n into 1 plus J omega n. So any queries still here? Okay, so I'll proceed further. Okay. So what have they done is KL, which was over here, FMV and KI, KL is FMV and KI on 1 minus T squared. They have also included omega RHP as well. Okay, they have included omega RHP. So they get effectively K loop of J omega n to be KL into J omega n, 1 by J omega n into 1 minus J omega n upon 1 plus J omega n. So this is, you see, this is a complex quantity. It is a complex quantity. It can be divided into a real part and imaginary part, or the magnitude and a phase angle. So my R upon omega n is given by KL upon mod of omega n into mod of 1 minus J omega n upon 1 plus J omega n. So my R of omega n will be equal to KL, omega n is positive, so omega n into square root of 1 plus omega n square divided by square root of 1 plus omega n square. Because magnitude is what? The real part square plus imaginary part square. So it comes 1 plus omega n square divided by square root of 1 plus omega n square. So these two get cancelled. So that is why I have wantedly made it to be of this form. Okay, so my R of omega n will be equal to KL of omega n. Similarly, my angle of theta omega n will be equal to, this J contributes minus 90 degree. Okay, then minus of tan inverse of the imaginary part. Okay, minus 90. So there are three complex quantities. So these complex quantities will create the angle. So J creates minus 90 degree. So this will, the zero, this RHP 0 will create a angle which is given by minus tan inverse of the imaginary part is minus omega n divided by real part is 1. And then because this pole is in the denominator, it will be given by minus of tan inverse of the imaginary part, J omega n. No, J will not come, just be omega n divided by 1. So effectively, I will get my angle to be minus 90 and minus comes out. So minus tan inverse of omega n, and this is minus tan inverse of
2 tan inverse omega.
Yes, so minus 2 tan inverse of omega. Okay, so this will be minus 90 minus 2 tan inverse of omega n, which is also written as minus 90 minus tan inverse of 2 omega n upon 1 minus omega n square. Okay, it can be written in this format also. Tan inverse of A plus tan inverse of B can be written like this. Okay, so this is how I've got my, someone else saying something? So this is how I represent this complex quantity into a real part and an imaginary part into a polar form into the magnitude as well as the phase angle. Now, if I want to find the phase margin, okay, I want to find the phase margin. Phase margin is given by 180 plus my angle. Okay, so that is 180 minus 90 minus tan inverse of 2 omega n upon 1 minus omega n square. That becomes 90 minus tan inverse of 2 omega n upon 1 minus omega n square. So by selecting omega n, so what I can do is I can set the phase margin to be 60 degree, and then I can find out which omega n will result in a phase margin of 60 degree. And once I find omega n, then I can find out my KL. Okay, my KL. KL is what? KL. Okay. So if I find out omega n, once I find omega n, then I also know omega RHP, etc. I know. Okay, so there's a phase crossover frequency. So my KL. Okay. So my magnitude. Okay, we know my magnitude R of omega n is KL upon omega n. So once I find omega n, okay, I find omega n, at what frequency it is omega n. I find out what omega n is my crossover frequency. Okay, my crossover frequency. Crossover frequency at which omega n it occurs. And at that frequency, this should be 1. So based on that, KL has KI in it. And from that, I will find out the value of KI. Once I find out the value of KI, then I also have the various other components. Okay, I will be able to find by pole zero cancellation, I will know what is K1, what is K2. Okay, K1 is given by this value, K2 is given by this value, tau D is given by this value. And then using both the back calculation, I can find Kp and I can find Kd. And tau D we know is given by 1 upon omega RHP. So this is the process by which we will find the gains, Kp, Ki, and Kd. So any queries in this? Or is the last part not clear still? So
So
there
here,
yes, yes, sir.
first, for the required phase margin, we are finding that omega n,
Yes,
and
yes.
using that omega n and substituting in the magnitude equation,
Mhm.
and we are finding the value of KL, and through that we can find KI, KP, and KD through
Yes,
K1, K2.
yes, yes, correct. Yeah. Okay. This is a bit of this is one method. Okay.
This omega RHP is the uh, omega RHP is the gain crossover frequency.
No, 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 no. That is not. This omega RHP is part of my GVT. And it is
Okay.
recommended that my crossover frequency should be around omega RHP by 3 or less than that, or omega RHP by 5, etc. Because what happens is this RHP 0. You remember GVT of S and this 1 minus S upon omega RHP. So this omega RHP will, in when it is, what it does is, if I tell the system to go left, it will initially go right because of my RHP 0. And because of this problem happening, because of the RHP 0, what we have to do is we have to slow down the system. We will slow down the system intentionally. Because what happens is, I tell the system you go left, it will go right for some time and then it will go left. So if I make the system go very fast, it might just go completely to the right. when I have commanded it to go to my left. So to avoid such a thing happening, we will reduce the bandwidth. Okay, we reduce the bandwidth. So omega c crossover frequency is my bandwidth. So what I do is I reduce the bandwidth to be less than the RHP0, and it just recommended for this PID, for this voltage mode control PID controller, we select the crossover frequency to be less than 1/3 of the RHP0, or like 1/5, etc. So that the speed at which my system, my loop will respond is lesser than the RHP0. So the RHP0 effect will come, and then finally it will go to the correct direction. Okay.
Okay.
So this is a problem with the boost converter. Why we cannot increase the bandwidth of the boost converters? Because of the RHP0. The RHP0 puts a limit. This RHP0 was not present in the buck converter, but it is present in the boost converter, and controlling the boost converter is difficult. So this is one of the hurdles we faced for a boost converter. So this is how we will design in analog voltage mode control. We design the PID controller gains, etc. Now we will go to the digital domain. What happens in a digital domain is the loop remains almost the same. This is the analog loop. GC, FM, GVD, etc. all are same. Only we add this delay. Okay, this is the delay which is added. That delay stands for my ADC delay plus my DPWM delay. Okay, all this is clubbed together within this. And taking that into account, we will proceed with the same procedure. We will follow the same procedure which we followed earlier, but we will incorporate this E minus S tau D. Okay. So can anyone tell me what is the magnitude of E minus S tau D? So this E minus S tau D, what we do, S we will replace by J omega. So it will become E raised to minus J omega tau D. It is of the form cos of omega tau D minus J of sine. So when we find the magnitude of this, it will be square root of cos square omega tau D plus sine square omega tau D. So that is equal to 1. Square root of 1, so it is 1. So this has a magnitude which is equal to 1. So e raised to minus S tau D can be represented, no, sorry, e raised to minus J omega tau D as a magnitude 1 into some certain angle. So the angle, how we find it is, this angle is, this is my part, right? So it is the tan inverse of the imaginary part for the real part.
Minus tan inverse of tan D.
Yes. So it comes out to be minus omega tau D. So this is the phase, the angle. So it is minus omega tau D. Okay. So any queries? Okay. So this is how this is what we must incorporate in our loop transfer function. So that is what they have shown over here. So what is this step? Okay. We will set the gain crossover frequency omega c to be a fraction of the RHP0. My crossover frequency or my bandwidth is set to be a fraction of my RHP0, k less than 1. It's recommended value, empirical value by previous designers. They have found it recommended good response, k equal to 1/3. So I set that. Okay. Once I set that value, okay. Once I set that value, my phase margin will be 90 minus tan inverse of 2 omega n upon 1 minus omega n square. At which omega n? At omega c by omega RHP. and minus omega c tau d. This is what? This is my due to my delay. Okay, this is due to my delay. This is not my derivatives tau d. This is due to my delay. All right. So in the previous analog case, this part was not there. In analog domain, this part was not there. But when we went to digital control, because of the delay in the ADC, the delay in DPWM, etc., there is this component which will try to reduce the phase margin. Okay, it will try to reduce the phase margin. So that is one disadvantage of digital control. Like analog control is faster. Like there's no delay. The delay is less as compared to digital domain. So what we do is we will take the tau d which is given and we will see whether the phase margin meets the requirement when we substitute over here. And if the phase margin is greater than 45 degree, we are happy. But if it is not greater than 45 degree, then what do? We reduce k. We will make it k equal to 1/4. Then we will find the phase margin. And then we will again check. We will keep on repeating till we find the phase margin to be of a value greater than 45 degree. And then we will find ki. Okay. So any queries in this part?
So this omega n is the omega n.
Omega n is
This is the
this the
it is the what frequency, sir? It is a natural what frequency it is?
It is a normalized frequency. It is a normalized frequency. Omega n is omega.
Oh, that's why we are normalizing.
Just like sort of normalization thing which we are doing to simplify our design. It looks neater, etc. And phase margin is found at the crossover frequency. So that's why we substitute here at omega. We put omega equal to omega c. Yeah. And then we substitute into this equation.
This bandwidth.
Yeah, bandwidth.
So compared to analog in digital, this minus omega c into tau d will come in phase margin equation.
Yeah, it will come and it will reduce the phase margin because of the delay.
Yes.
So it is like sort of deteriorating the response of my system.
For the same bandwidth, the phase margin will come down for the same crossover frequency.
Yeah. Well, what let's say? For the same crossover frequency, yes. The same crossover frequency, you are reducing the phase margin gets deteriorated, becomes less. Yeah. So what happens is if we set the bandwidth of both analog control and digital control to be the same, the phase margin of digital control will be less than phase margin of analog control. Then what do we do is we found for digital control the phase margin is less. We want the phase margin to be greater than 45 degree or to be around 60 degree, etc. So in that case, what do we have to do is we have to reduce the bandwidth of digital control. We'll have to reduce the bandwidth further. And when we reduce the bandwidth, then we will get a phase margin which is meets our requirement. Okay. So when I'm saying I'm reducing k means I'm reducing my bandwidth effectively. So any other doubts?
Sir, this k is that how we are choosing this to be 1/3?
1/3 is like a standard thing. It's like a starting iterator value we take. Okay.
Okay.
So because it has to be less than RSP0. So such a value has been shown to show good response.
Okay. So we can reduce to 1/4.
Yeah, we can reduce to 1/4 also. we reduce to 1/4, the bandwidth is less and the response will not be as fast as we want. It becomes slower response. So then we find Ki, and once we find Ki, then you can find all these others, K1, K2, we can find our Kp, Ki, Kd, etc. We can find out. And then we can convert it to digital. Kp remains the same in analog and digital, but integral gets multiplied by the period of the controller update time period, and derivative is divided by the controller's update time period. Okay. So like that, using pole zero cancellation, these are the formulas. Okay, you can remove these formulas, and so this meeting will end in around 10 minutes. Okay, so then we will again start the meeting. So these are the values. You will have to remember these formulas, or else in the exam you will have to derive it. Okay. Then this is how we convert from analog domain to digital domain. And there's another method known as alternative design method. So this is another way how we can set a KP, KI, KD. So that also you can look into, and that also has been demonstrated by Sir in the lecture 45, lecture 46. So I wanted to know which assignment are you guys currently submitting? No. Which assignment are you going to submit now? Like which assignment submission is due on this Wednesday?
5, sir, 5.
So you have to submit assignment 5 this Wednesday.
Yes.
So, and Dr. D. Vanita, do you have any queries? Okay, so I will proceed with boost converter current mode control. So now we have studied how do we design the gains for the in case of voltage mode control. Now we will consider how do we design the gains instead of in the case of current mode control. So this is the block diagram. We have a reference voltage and then output voltage, and the error again goes. So in both cases, the error voltage is going to be my controller. But in this case, my controller is different. Here, my controller is generating my reference current. My reference current is compared with my inductor current. And that is how effectively I am generating my duty ratio. So this is where the set pulse comes. Set pulse will come over here. It comes over here. The set pulse comes, and the set pulse comes, Q becomes high, Q becomes 1. And this goes high. Okay, it goes high. And it will continue to remain high until my inductor current tries to become more than my reference current. And when my inductor current tries to become more than my reference current, then a reset pulse comes. And a reset pulse comes over here, and that will turn off my switch. Okay, so this is the simple operation of peak current mode control, and this is an analog domain. Okay. Now we want to do the current mode control. So when we're doing current mode control, we will see the small signal block diagram. So similarly, how we did for voltage mode control, we will do for current mode control, and my loop transfer function changes. Okay, here my loop transfer function only consists GC and GVC. So K loop of S is equal to GC of S into GVC of S. Okay. And we know one more thing. Right? GBC of S is equal to KG 1 plus S upon omega ESR into 1 minus S upon omega RHP divided by 1 plus S upon omega P. Okay. And this omega ESR, all these values are given over here. Kg is given over here. Omega ESR value is given over here. RHP 0 value. And the pole frequency. If you notice, 1 RC into C will be very high. So that's ESR 0. That is, so there are two zeros. Okay, there are two zeros and one pole. And this 0 tends to infinity. This tends to infinity, the 0. Because omega ESR is very, very small. No, wait a minute. This omega ESR tends to infinity. Okay, it is a zeros located at infinity. So what we can do is we can neglect the impact of the 0. We can neglect the impact of the 0, and it will have negligible impact on the response of my system. Okay, so that can be neglected. So effectively, GBC of S can be written as Kg to 1 minus S upon omega RHP divided by 1 plus S upon omega P. Right? Now my controller, I have to design a controller for this. So in this case, a PID controller is not required. We can just use a simple type 2 compensator. So type 2 compensator is given by 1 plus S upon omega CZ and 1 plus S upon omega CP into S. So this is a type 2 compensator. This type 2 compensator has 1 0 and 2 poles with 1 pole at the origin and just 1 pole over here. Now using this, we want to shape. We want to shape the loop. We want to shape the loop. So what we do is this is negligible. Okay, this can be neglected because omega ESR is at a very high frequency. What we do is this is my RHP 0. We set the omega CP to be equal to omega RHP, like the same way we did for a boost converter. What we do is we set omega CZ to be equal to omega P. This to be equal to omega P. So that occurs, what will happen is will be K loop of S equal to Kg into Kc to 1 minus S upon omega RHP divided by S into 1 plus S upon omega RHP. Right? And we, as I've explained, why we go for placing this one at this point to make it magnitude 1. So this is all shown over here. And similarly, we take omega n to be equal to omega upon omega RHP, and we will get the magnitude part and the angle part we will get over here. And this is the similar angular contribution which comes over here. So what do we do is at the grain crossover frequency, omega c, at the gain crossover frequency, this value is 1. Okay. So from that, we will get the value of KL. Once we will get a value of KL, we also have the phase margin is given by this format. So there are two options. We have two options. Either we select phase margin and then we will calculate omega n, or we select omega n and we will calculate phase margin. We can go by any of these procedures. We just select phase margin and we will get omega n, or we will select omega n and then we can verify that if the phase margin is sufficient. Okay, the phase margin is sufficient. If it is not sufficient, we have to change our omega n.
Sir,
Yes, yes.
Sir, usually how we are saying that that omega ESR is very high.
Okay. Okay, omega ESR is given by 1 upon RC C. So this is my omega ESR. RC into C. RC will be around 5 million. So 5 million. Capacitor, take capacitor like take it 100 microfarad. So it is 100 into 10 to the power minus 6. So omega ESR will be equal to 1 upon 500 into 10 to the power minus 9, or it is 10 into 10 to the power 6 upon 5. So it is around 2 into 10 to the power 6 radians per second. Okay. This is a very high value. So it has a negligible impact. Okay, negligible impact on response.
Okay, sir.
Any other queries? So we can either select the crossover omega n, or we can either select phase margin, and then both other possibilities, and then we can design. We can again find the the transfer function. We'll find the transfer function of the controller. So we will also solve one sum, and then this process will become a bit more clear to you. And a digital controls similarly again. The delay comes into the picture. This delay comes into the picture. Actually, this is a wrong diagram. This is for current mode control diagram. So this has to be GBC, and this FM will not be there. Okay. So we have to follow the similar procedure. And again, like how we did in voltage mode control, what happens is this one comes. Again, the delay affects the phase. Okay, the delay further reduces the phase, and that has the response. And in a similar manner, we can do the iterative process to find the response of the system, the gains of the system. So using this method, we will get this transfer function. Okay, this is the transfer function of my type 2 compensator. This is the transfer function of my type 2 compensator. It has a 0, one pole at origin, one pole at some value. Okay, what I will do is I found this omega's, the pole I've placed at the RHP 0, so this is the value of it. The 0 I place at the pole of the GVC, so that is the value of it. And this Kc I find from the crossover frequency, I find the value of Kc, and this is given by this value. Now all of this is in analog domain. All of this is in analog domain. So to convert it to digital domain, I will replace S by this value 1 minus Z inverse upon T, and I will substitute over here, and this will be the transfer function I will get. All right. So any queries in this? If there are no queries, we can proceed further. So I have made a sample question. Okay. So let us consider a boost converter. Okay, it has the following parameters. Input voltage is 3.3 volt, output voltage is 5 volt. My inductance is 2 microhenry, capacitance 100 microfarad. My ramp voltage is 10 volt. My load resistance is 1 ohm. This my ESR capacitance, and this my switching frequency of 500 kilohertz. So when I'm doing voltage mode control, okay, and I'm doing pole zero cancellation, and I selected the crossover frequency, I set my crossover frequency to be omega RHP upon 4. Then what will be the phase margin I will get? Okay, that is the question. So if you remember, so can anyone tell me how to solve this? Remember, this is for voltage mode control. So you see my phase margin is where 90 minus tan inverse of 2 omega n and 1 minus omega n square. Okay. So what will be my omega n? Can you tell me?
Omega C by omega RHP.
Okay. So what will its value be?
Okay.
Hmm?
0.25.
Yes, 0.25. So what will be the phase margin? So omega C is 0.25 omega RHP. So what is the phase margin you're getting? Do you have a calculator with you?
So it is some 2.38 because it is sorry.
It should be in degree. Your calculator should be set in more degree, not radians.
61.92.
Phase margin 61.92. Okay. Now assume omega C is omega RHP by 3. Then what will be the phase margin I will get?
.33.
So what will be my phase margin?
Three point four seven.
Hmm? It should be in degree.
Yes, sir, it is 53.47.
Oh, yes. So it will be 53.47 degree. Yes. Okay. Similarly, now we will consider a sum with peak current mode control. What we will do is, now you have to find we just saw about current control, how we will design the controller. Okay, now we have till now not added any delay. We're just simply doing for the analog part. Okay, so these are my parameters. I want you to find this one. So if you will remember, this is my GBC of S is kg into 1 plus S upon omega ESR 1 plus S upon 1 minus S upon omega RHP divided by 1 plus S upon omega pole. So can you calculate kg? Okay, my kg, the formula for kg is equal to R into 1 minus D upon 2. Omega ESR is given by 1 upon RC into C. Omega RHP is given by R into 1 minus D square upon L. And omega P is given by 2 upon R plus 2RC into C. So can you calculate these values and tell me what will be those values? So what will be the first step?
Finding duty ratio
Yes.
0.34.
Duty ratio is 0.3. Okay, correct. Then
kg 0.33.
kg you got it. kg you got 0.33, correct? Yeah.
Omega ESR is 2 into 10 to the power 6.
Okay.
P 217800.
217,
800.
correct. Then omega P
1.98. Oh, into C. Sir, omega P is 2 by R plus 2RC into C.
yes.
Is 19802 omega P.
Okay, 19802. Yes. So these are the location of my poles. My pole is located here. My RSB 0 is located here. My ESS 0 is located over here. Okay. So this is located at very high frequency. Omega ESR is located at very high frequency. It is more than 10 times frequency of the RSB 0 and the frequency of the pole. Okay. So we are neglecting the effect of the ESR 0. Now, what do we have to do now? So we have found out. Now we have to place a controller. Okay, my controller. How I place my controller? It will have value of Kc. Okay, Kc will be there into 1 plus omega s upon omega Cz upon 1 plus s upon omega controller pole. Now, what will be the value of omega controller pole?
9802. Oh, sorry. It has to be 21780.
Yes, it should be equal to omega RHP. So it will be 21780. Then my omega CZ, what will be the value of omega CZ?
Oh, it has to be 19802.
Yes, it will be omega P, so it will be 19802. So now we have found this and we have found this. So now what is remaining?
AC.
KC. Okay, so we need to find KC. So how will we find KC? Now, when we will do the pole zero cancellation and everything, we will get the magnitude of GBC J omega to be equal to K into G upon into Kc upon J omega. Okay, sorry, I forgot this pole. There's a pole at the origin over here. So when we do pole zero cancellation, this zero and this pole get cancelled, and magnitude of this is same as the magnitude of this, so they do not come into this picture. So the magnitude of this will be Kg into Kc upon omega. All right. Now what is my, and this omega, okay, and at the crossover frequency, let us make me write over there, GBC J omega is Kg into Kc upon omega. At omega equal to omega c, we have magnitude GBC J omega is equal to 1. That means Kg into Kc equal to omega crossover frequency. So my Kc is equal to omega crossover frequency upon Kg. So what is my crossover frequency? It is given to be 1/3 of the RHP0. So that will be omega RHP upon 3 into Kg. So my omega RHP is 217,800 divided by 3 into Kg. What was the value of Kg?
0.33.
Kg is 0.33.
0.33.
So you can calculate now. That comes
Yeah.
to 20,000.
That
No,
22140.
Mhm.
Yeah, correct.
2.40. Yes, it's 2.40. Okay. So any queries in this part? So I hope you understood how we are designing the controller. So this is simply for analog voltage mode control, analog current mode control. But okay, and in this case, we have not considered phase margin. So if we want to check if our response is like giving good suitable phase margin, no, we check now if omega RHP is omega crosses omega RHP upon 3, then we get some sort of phase margin like this. So similar magnitude we will get. Okay, we will get some phase margin around 53.47 degree. Right? So we will get a phase margin. Oh, sorry. We will get a phase margin of 53.147 degree. But in case of digital, when it goes to digital, okay, my phase margin will be 53.147 degree minus omega crossover into my delay, tau d delay. That will reduce my phase margin. Okay. So let us assume our delay is 1 microsecond. Okay, 1 microsecond. So then what will be the phase margin new? Phase margin for digital domain. What will be the phase margin then?
Should we change into degrees, no, sir? Omega C into tau d in radians.
Um, no. Okay, okay. Yes, it has to be changed into degrees. Yes. Will also be changed to radians. So it will be 53.147. See, omega C is, that's omega C. Omega C is 217,800 radians per second. So when I do omega C into tau d, I will get 0.217,800 radians. Because this is 1 microsecond. When I multiply it, omega C into tau d will be 0.217,800 radians. That I have to convert it into degrees. So it will be 0.2178 into 180 divided by 5, which comes out to be around
12.47.
12.48 degree. Okay, so I'll do
Okay, nice.
12.48 degree. So that will be around 40.66. 40.668 degree. Okay. So in this manner, you will get sums, and I hope with what questions I have taught today, you should be able to solve these sums. Okay, and another very important thing is the PID. You will get the PID, you will do the tuning, you will get KP, KI, KD. These are in analog domain. Okay. So in digital domain, they will say you convert it to digital domain. When you have to convert in digital domain, KP digital remains KP. KI digital is KI into TS. And KD digital is KD upon TS. Okay. So this also is a very common question. So yeah. So I'm hoping with this background, you should be able to solve the assignments and to be able to do well in the exam. So is there any other queries till this part? Doubts, queries?
Sir?
Yeah.
Sir, the compensator here, PID, the compensator here we are using is type 2 compensator.
Yes, type 2
in our previous discussion.
Hmm.
That 1, 0 and 2 poles.
Yes.
Sir, what are the other types of compensators available as a whole?
Okay. So
Is
there's
that, but is there a type 1 compensator?
yeah, type 1 PI controller is a type 1 compensator. So there's a type 1 compensator. It's like a PI controller. It's KP plus KI by S. So it has KPS plus KI by S. So it is KI into 1 plus S by KP upon no, so equal to KI into 1 plus S KP upon KI by S. So it is written KI into 1 plus S upon omega controller 0 by F. So it has 1, 0 and 1 port. So this is a type 1 compensator. A type 2 compensator has K into 1 plus S upon omega CZ upon S into 1 plus S upon omega CP. Okay, this is a type 2 compensator. Let us see a type 3 compensator. Type 3 compensator is given by K into 1 plus S upon omega 0, 1 into 1 plus S upon omega 0, 2 from S into 1 plus S upon omega pole 1 into 1 plus S upon omega pole 2. Okay. This is a type 3 compensator.
Okay.
So there is actually a very excellent TI document by Texas Instruments, okay? By Texas Instruments about, understanding these compensators. It's a very good document. You can refer to that. Understanding type 1, type 2, and type 3. compensators.
So we can just Google the compensator by Texas instrument.
Yes, you will get a document. Okay, it's a very good one, but it'll take time to understand.
So one pole,
Yeah.
okay.
Yes. Yes.
So roughly we can say if it is one pole and 1 0, it is type 1. 1 0 and 2 pole, it is type 2, and 2 zeros and 3 pole, it is type.
But one pole has to be at the origin. Okay, that is the one
Okay.
to keep in mind. It's not just any pole. One pole
All
has
the,
to be.
in all the cases.
Yeah, all the cases. Yeah. So this is done. Next, we will go on to time optimal control. So we will consider time optimal control. So what is time optimal control? This is a buck converter, all right? This is a synchronous buck converter. Both switches are controlled. This is the previous operating point. This is my previous my point. So this is my operating point. Now I want to go to this operating point. My output voltage will remain at the same value. It should stay at the reference value. It will remain at the same value. But my inductor current must go from this state to this state because my load has changed from this value I0 to I0 plus delta I0. Okay. So my VREF is not changing. My output voltage, I want it to be regulated at this value. So see, if you see, this is these circles over here, they are known as the trajectory of the converter. So when it is on, okay, when the switch is on, when S1 is on, it will go like this. It will go. Then when S2 is off, it will go like this. So this is how it will be rotating continuously in steady state at this operating point. Then I want converter to go from this operating point to this operating point. And in this operating point also, what will happen? It will when the switch is on, it will go like this. And when the switch is off, it will go like this. So it is the average value of my waveforms will be at this operating point. But at all instants, it is not the value of the inductor current and output voltage is not at this point. So they are like, they are varying around this point. And that is how this buck converter and boost converter works. They are a switched system. They're a switching system. Okay, it is either on or off. Okay. Now what I want to do is I want my controller to go I want my response to go from this point to this point in one switching cycle. That means it will if it works as per my design or as I desire, then it will start at this point. It will go when the switch is on. Inductor current will keep on increasing. My output voltage will fall a bit. It will come to this point, and then my switch will be turned off, and it will start falling. It will follow this trajectory and will come over here. Okay, and then it will get then it will oscillate around here. Okay, it will move around here. So this is how the operation works. So this is known as time optimal control. That is in one switching cycle. In one switching cycle, I am able to go from this operating point to this operating point. And this was reported by this paper, W. Burns and T.J. Wilson. Right.
One steady state to another in one switching cycle.
One switching cycle. So usually, actually, what happens is it will not go. It will like if you will see further. So what happens is over here, if we see in the time domain, the inductor current was actually operating over here. then it will go and it will start operating like this. Okay, this is my inductor current waveform, and my output voltage waveform, it was at a regulated value, then it will reduce, and then it will come back over here. Okay, so this is my the response which I want. But what might happen, like, but if it was not this time optimal, what would happen is it would be operating like this. It would go like this, 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 like this, like this. It might go up over here and it might come like this. This might be the response. This response would further be like reduce and then come like this sort of response. Okay. So this response is not the response I want. In my response, I want it to immediately go from one time to the other time. It should go very fast. So this is known as time optimal. Okay. This is a quite advanced concept. So there are ways in which we set some sort of switching one switching boundary, and based on that switching boundary, when the controllers are tuned appropriately, then it can achieve this operation, right? And if such an operation occurred, okay, such an operation occurred, then what happens is the peak current. This is my peak current. Okay, this is my peak current. That can be derived to be of this format, of this equation. Then the recovery time. This is my recovery time. It can be derived to be of this, and my voltage dip. This dip in my voltage is derived to be of this. Okay. So this is for a load step transient. This is for load step transient. And the load was initially operating at this point. Now it is stepped to this point. So this is how the waveforms are look like, and this is how, based on some analytical calculations which were shown in the lectures, these parameters have been defined. So we want the recovery time to be less, peak current to be less, voltage undershoot to also be less, but they are determined by these equations. Okay. Then we will consider the case where my reference is changing. Initially, in this case, my reference is fixed. My output voltage, I want it to be regulated over here. Okay. But my inductor current is changing from this point to that point. In the next case, in this case, I want my reference value to change from Vref1 to Vref2. Okay. But my inductor current will have the same steady state value. But the inductor current waveform is not shown here. The capacitor current waveform is shown here. And then when you derive these equations for the peak current and the recovery time, it will come in this format. So when we compare for a reference transient and for a load transient, this is how the peak current is determined, the recovery time, and the voltage undershoot. In reference transient, there's no voltage undershoot. So if I want to reduce the peak current for a reference transient, I would have to reduce my capacitor. I have to reduce my capacitor and increase my inductor. And if I want to reduce the recovery time, I'll have to reduce my capacitor and reduce my inductor. All right. But for slow transient, if I want to reduce my recovery time, I'll have to reduce my inductor. And if I want to reduce my voltage undershoot, I have to reduce my inductor and increase my capacitor. So from this, what do we get is, in this one, we have to reduce the capacitor. In this one, we have to increase the capacitor. But we cannot do both. So it's like a sort of trade-off. It's like what is more important in our application, whether load transients are more frequent or reference transients are more frequent. Based on that, we have to decide a suitable value of L and C, right? Next, large signal tuning. So this is a boost converter's vector field, all right? So this is when those These green curves is when the switch is on, and these blue curves are when the switch is off. So it is at this point, inductor current, the output voltage is at this point, the inductor current is at this value. Okay, it is at this value. Now the switch is turned on, inductor current rises. The output voltage of the boost converter falls and falls to this point. Then it reaches the switching boundary, and then the switch is turned off, and then the trajectory follows like this point and comes over here. Right? So this is for a load step up waveform trajectory viewpoint. It is shown like this. Right?
This is that.
This is what?
Sir?
Yes.
Sir, this behavior is similar to the steady state operation and the time optimal control.
Yeah.
That
yes.
circle.
Yeah. This circle.
So are they? Okay. So they are same.
Yeah, they're same. Yeah.
That circle when it is operating in steady state and
see that circle was for a buck converter, but for a boost converter, when it is on, it is a little bit of a linear thing, linear reduction, and then like this format. When you solve the differential equations, you will get to know how it is varying with time. So, but what happens if you change the slope? If the slope is changed, then it might not reach steady state in one switching cycle. It might go further down and come up. But we want it to come here directly and go like this. So that depends largely on the what you see the slope of this switching boundary, right? And this is denoted by something known as a first order switching surface, which is given by this equation. And this also can be done by current mode control with the normalized load current waveform, right? And these are certain experimental results which have been shown. And what we want is we want to find a good proportional gain, the optimal, which will give us a good response. Right? So similarly, these things are there, various switching surfaces, etc. Okay. So the goal of this is, what is the goal? We are at this, so this is for a buck converter. We are at this operating point, we are going to this operating point. And we have this switching surface. This switching surface is the inductor current minus the reference current plus my proportional control into output voltage minus the reference voltage. Okay. So this slope is given by minus Kp. Because this is the slope of voltage, this is the slope of current. Okay. If you do, so this is the slope Kp, all right, for this line, which is my switching surface. But I want there to be a hysteresis band. Okay, some certain band is there. Either it can be forcefully made or it can be made because of the actual switching operation or actual PWM operation, set points, reset points, etc. It can be inherently done, or we can use hysteresis control and forcibly create this sort of band. So it starts at this operating point and reaches this operating point. I want that to occur in one switching transition. And for that to occur, I have to tune my Kp accordingly. Right. So I will tune. Another thing to note down is my control. This is Vref minus V output. Right. We initially showed only Kp into Vref minus V output. We neglected the integral term, and integral term is neglected because it's so this integral term does not come into the picture in the transient part. So this going from here to here and coming back here is known as the transient behavior. In that, the integral term has negligible impact. So we ignore that. So we tune the Kp using the large signal trajectory. Okay. But in the steady state, the steady state operation over here. Okay, the Ki is used to reduce the steady state error to bring the steady state error to zero. Okay, the steady state error, we want to reduce the steady state error. So it operates in the steady state. So to do that, we use the small signal model. Initially, we found out for voltage mode control and for current mode control, after pole zero cancellation, okay, we find the value of Ki, and from that we find the value of Kp, Kd, etc. that we did. But here, we find the value of Kp, we use that value of Kp, and Ki value is found from the small signal model based on what phase margin we want, what crossover frequency we want, etc. All right. So we find the value of, so from that integral gain tuning we do using crossover frequency Ki. All right. So similarly, these are the waveforms for load step-up trajectory. How the inductor current was first operating at this range. Then when you give a step, it starts rising like this and comes here. And the output voltage will have a dip. That dip corresponds to this. Okay, this is my dip in the output voltage. This is my dip in the output voltage. So it will reach this point ILB1 from this I01 Vref point. It will go to V1 I1 like this. Then it will come to this point I02 Vref over here. Okay, so using the off-state trajectory. This is my on-state trajectory. This is my off-state trajectory. Okay, if you want further details, you can refer to lecture 15, the previous NPTEL course. So similarly, they do these PID controllers, PID tuning is done for buck converter, etc. These are certain formulas which you can keep in mind. And what happens is sometimes the gain Kp is very large. That might not be feasible in operation. What they do in that case is you multiply with some K attenuation factor to reduce the actual effective value of Kp. And if we are doing the multiplication of Kp by some factor, we have to even multiply Ki by that same attenuation factor. Okay, so these are certain stuff are there. And then similarly, you can find the PID controller gains, etc. Next is we'll consider pulse frequency modulation. So what is pulse frequency modulation? It is also known as PFM. This is a light load technique. So in light load condition, what happens is PWM, pulse with modulation of fixed frequency. Okay. Can you tell me what are the losses which occur in the buck converter?
Yes. So switching loss and then conduction loss in the switch, and then ESR in the capacitor.
Yes. So
And then in
the dominating one is the switching loss and the conduction loss. Okay. Now, at light load means the output current is low. If the output current is low, the inductor current also becomes low. That time, so the conduction loss, peak conduction loss also reduces. That is good. But if we are operating at a particular switch fixed, so what happens is also at light load, what happens? The output power also has reduced. And if you are operating at the same frequency, my switching loss still remains same. Okay, switching loss still remains same. So what can happen is my switching loss is a lot, although my conduction losses have reduced, but my output power also has reduced significantly. So what is happening is my efficiency will become poor. My efficiency will become very poor because the magnitude of the switching loss is quite high. It's like quite a high value as compared to the output power. Okay, we don't know the exact ratio, etc., but it dominates the losses and it is a very high value. And so it will cause a reduction in the efficiency. But in normal high load condition, in high load condition, what happens? My output power is high. So my output current also is high. So my inductor current also is high. My conduction losses also are high. But my switching losses remain the same. They remain the same. because I'm doing pulse width modulation, and this is fixed frequency. Okay, this is for fixed frequency. So in this case, what happens? Even though the switching loss is there, the conduction loss also is increased, the losses, the magnitude of losses is not comparable to my output power. Okay, so my efficiency will be quite high. But in this case, because my output power is reduced a lot, but my switching losses are don't reduce. So my losses are comparable to my output power, and so my efficiency is poor. And so the reason is because of this switching loss. So if I want to reduce the switching loss, what I have to do is I have to reduce the switching frequency. When I reduce the switching frequency, my switching loss also will reduce. And that way, at light load condition, I can improve my light load efficiency. So any queries in this?
Sir, in high load condition also, the switching, when we are switching, since the load is high, the magnitude of current, magnitude that the current is reaching for each switching is higher.
Yeah, yes.
So switching loss will also be higher in high load condition. Is it,
Okay.
or compared to conduction loss, it is somewhat inferior?
Actually, if I'm not mistaken, switching loss is directly proportional to switching frequency square. It might be directly proportional to the output. See, I have to verify this. I'm not exactly clear. But my switching loss, I think, is related to current and switching frequency square. So at high load, this is lots. I agree, this is lots. Okay, so let us consider at what happens is this has some impact, but the switching frequency has a higher impact. Okay, so if I reduce the switching frequency, it will reduce the losses. I am not saying that the switching frequency loss for high load is the switching frequency loss for high load will probably greater than the switching frequency loss for light load. Okay, because the current over here is more. In high load the current is more. In light load the current is less. But what I am saying is, as the output power is becoming low, okay. See, assume it was output power was 100 watt. Okay, 100 watt. And my switching loss is like around 0.5 watt. Then it has negligible impact on the efficiency. But suppose my output power becomes 10 watt and my switching loss is still 0.5 watt. Then it is quite a significant chunk as compared to my output power, right? So in that case, it becomes needful for me to reduce this switching losses. And if I want to reduce the switching losses in that case, see, it might not be 0.5 watt because the current has reduced, it might become 0.4 watt. Okay, but if I want to further reduce it and make it like around 0.1 watt, then I have to reduce the switching frequency. So there are.
Sir,
Yes,
you mean to say at light load, switching loss will be dominating the efficiency?
Yes.
At a high load, conduction loss will.
Yeah, this is for the usually designed convention actually. Okay. So see, if you see a mobile, this is an example which is very practical, which you can understand. It is not always operating. Okay, there are some times when it is in standby mode. That time I don't want it to. So that time it is not operating at full load. Okay, it's not operating at high load. Now, suppose you're seeing Netflix or something. as well as you're listening to music or you're downloading video, etc. The time it is a higher load. Okay, more current will be drawn, more loss. It will be like that. But when it is at light load, I'm hardly using my mobile. It's just on standby. And still, if it is operating with high switching frequency losses, then it will drain my battery. So I don't want that to happen. So in that case, when it is at light load, they use light load techniques, light load control techniques, light load modulation techniques, so that the losses will be less. And you see, like many of these devices, like smartwatches and other gadgets, 90% of them, or a vast majority of the time, they're hardly operating. They're just on standby. And if they are on standby, and that time the losses are still quite comparable, are still quite high, uh, as to when they are actually operating and in use, then it is draining my battery unnecessarily, even though it is not operating even though it is not required, it is still draining a lot of the battery. So they use these pulse frequency modulation, other constant on time control, also certain techniques to reduce these losses, okay, at light load. So one of the main concepts of these light load techniques is you reduce the switching frequency. Effective switching frequency you are reducing.
So based on the loading condition,
Mhm.
which loss needs to be reduced will be decided.
Yeah, yeah, yeah. So like they might
So
use
based
what, which is telco.
so based on that, this modulation technique will be selected based
Ah,
on the loading condition.
yes. So maybe at light load they may use this pulse frequency modulation. At high load they use pulse width modulation. Like that they can use. They can operate. Okay. So now I'll just give a brief
Yes.
recap of how it works. What happens is, just assume this one, okay? This pulses. They're like the normal pulses which we get using closed loop control. Okay, using closed loop control. These are the pulses which we get. Okay, these are the pulses. QP is these are the standard pulses which I get. Right? But I am seeing my output voltage. I'm monitoring my output voltage. If my output voltage is less than my reference voltage, what does it mean? If my output voltage over here, okay, so okay, I'll just explain one by one. This is my sampling clock. At this time, I am sampling my output voltage. Okay, this is my sampling clock. I'm taking the samples. This is my switching clock. It is coming at a fixed frequency. And when the switching clock is coming, my pulse is going high. And based on particular control loop or open loop control, these are the pulses which are generated. Okay, these are generated pulses. And if this pulse skip modulation technique was not present, then this would be the pulses. This would be my gate pulse over here. This would be my gate pulse Q. But I have added another layer of another sort of block, you can say, that when my output voltage is greater than my reference voltage, that is when my output voltage is greater than my reference voltage, then what I want is, I don't want these pulses, I don't want them to go, I don't want them to turn on my switch. I don't want them to turn on the switch because already my output voltage is more than my reference voltage. Here and here, my output voltage is already more than the reference voltage. So if I give these pulses, it will further increase the output voltage, and that is not what I want. So what I do is, when the output voltage is more than my reference voltage, I will disable this. Okay, my PSM will be zero. If my QPSM is zero, what happens is my QPSM is ANDed with QP, and my effective gate signal comes to be like this. Comes to be like this. So instead of the gate signal being this, I am getting the gate signal to be this. And if you will observe, it is sort of effectively reducing the switching frequency. Sort of effectively reducing the switching frequency.
Sir,
Yes, yes, yes.
but here we are considering the output voltage instead of the loading condition.
Yeah, correct, yes.
So,
Okay.
do you want to at the light load condition the voltage will be higher? That is what we want to understand.
No. It's not like that. It is not like that. It is just this is the technique. We're explaining the technique. There might be some additional logic which would enable or disable this pulse skipping based on the loading condition. To know the loading condition, you need to know the information of the inductor current, etc. That is not shown over here. Okay, that is not shown over here. Here I'm just showing the concept of how pulse skip modulation works. Okay, the logical block diagram.
Okay.
Overall intelligence of when to choose, that all is not shown here. Right. So just assume that this is a light load condition. See, if you see over here, the inductor current, this inductor current is discontinuous. Okay. It is discontinuous. If this inductor current is discontinuous, the average current will be something very small. This will be my average current. Okay. But in normal operation, the average current will be like this, like this, like this, like this, something like this. My current will be, and the average current will be of this value. Okay. So here it is actually operating light load. How it is intelligently detecting that, that is not shown here. But it is assumed it is operating light load, and how it will function is shown.
So the second one is the switching frequency. The second graph is the switching one. So it has reduced from FSW to Q.
Yeah.
Sir, one more question I have.
Yes.
In the current sensing,
Mm-hmm.
in the lecture, sir is saying, if we instead of why we should not measure the current through the capacitor with the resistor. The current to the inductor we are measuring with the resistor. Whereas current through a capacitor we should not measure using resistor. It will increase ESR. That is what is. And then beyond that, what will happen?
Beyond that, at least for boost converter, it is not recommended, because if you see, for boost converter at least, it is the capacitor current is minus I0 when the switch is on. This is for boost, this is for boost, and it is IL minus I0 when the switch is off. So what happens? It is discontinuous. The capacitor current waveform is discontinuous. It will be something like this. It will be actually this thing. It will reduce minus I0. When it turns off, it will go like this, and it will reduce further. Again, it will be like this. It will be some waveform like this. Okay.
Yes. It will have some flat wave at the negatives.
Yes, or something like that it is. I'm not exactly remembering. So it is discontinuous. So if it is discontinuous, then it will be not good for the sensing, right? Because discontinuity means very high frequency. High frequency it is. So that high frequency has noise, etc. Right. So that's why for boost converter, at least we don't use capacitor current sensing. For buck converter, I am not exactly. I don't know much. I don't know what this part is then.
Sir, in the inductor current waveform, for the on time, that peak point,
Yes.
the inductor current waveform, the peak point.
Sir,
is that a discontinuity? Is that peak point a discontinuity?
No, it is not discontinuity, because it is going like this, right? It is going, it is coming over here, and it is coming over here, like this it is. So the capacitor current waveform, if I'm not wrong, it is like, I don't exactly remember. This is the inductor current waveform. For a boost converter, if you will see, the output voltage waveform will be like this, it will be reducing when it switches on, then it will go like this and it will go like this. Okay. Then when the switch is off, it will again go like this, and then again it will go like this and go like this. So over here, it is suddenly going from here to here. It is suddenly going from here to here. So this is a discontinuity. But over here, it is not suddenly going from one point to another point. This is continuous.
Because there also, if we sense at that peak point, we will have more noise. That's what they say.
Yes, yes. No, actually, why they say at sense at the peak point is noises, there'll be the sort of ripple will be there. Okay, these are not shown in these waveforms, so these are idealized waveforms for understanding. But in actual converter, it turns on, and then because of the diode recovery loss, etc., there'll be sort of these oscillations also will be there. Okay, these sort of oscillations also are there. So if there are oscillations are there, then you're not correctly sensing. It is not proper. These are sort of, that's why I told, if you remember, I had mentioned in peak current mode control, there is this blanking period, etc. Something considered blanking period. That is, I don't want a controller to operate in this region because this is undefined, not defined. It is like some sort of random thing. Okay, it is like sort of not proper.
Unpredictable.
Yes, unpredictable. Spurious something. So we don't want. So we have a blanking period to look after that. So that is not usually shown in all these waveforms. So these are just ideal, just to give you a conceptual understanding. When we practically we will implement, we have to consider these things and proceed. So yes.
So in time domain, whenever there is the faster rise time, in frequency domain, it is of higher frequency.
Yeah. Similarly, there's for mixed signal peak current control, where this QP, instead of earlier our QP was these set of pulses. Now instead QP is derived from a sort of peak current mode control mixed signal logic. So it is just a similar operation, just the way this QP is generated is different. Rest all everything else is same. So if you have any other doubts, you can tell, or we can end the lecture today.
And no other doubts, sir. We can end.
Okay. Thank you. So I think there's peak current mode control that this blanking period, etc. This document I have shared it in the previous week's video. I have added the link for a good document to understand peak current mode control. Okay, it is a very big document.
Sir, in that PDF.
Yes.
Sir, in that presentation, you have, I think you are uploading last week. Week 4 is not there.
Oh, week 4 is not there. Huh? Okay. So I'll upload week 4. I'll upload week 4. I think we have forgotten.
Sir, this documentation which week? This document is already there. I will check, sir.
No, actually in the YouTube video.
This blanking.
In the YouTube video,
okay.
I have added in the description. I've added a link to that document. Okay, to understand peak current mode control. Okay.
Okay.
Okay. Thank you. So I'll end the meeting.
Yeah. Good night.
Good night.